Hey everybody, it's Dr. Jensen with CCJ3701 Research Methods in Criminology. You'll have to forgive me, I'm still a little under the weather, but it was important to me to make sure we get everything created. So those of you that want to start early on your material, you can do so. You'll have to forgive me if I have to cough a little bit during the lecture. I'll try to kind of keep it away from the microphone so you don't get this cough blasting in your ear. But by way of announcement, this is your last week of heavy-duty statistics stuff. So this is our last technique we're going to learn. We have a few other small things we're going to do later, but this is the last big one we do. It's also the last lab you're going to do in this class. So you've been working really hard on your labs, and it's paying off. Hopefully you're feeling more confident, getting more experience, getting messy, making mistakes. Some people are even dreaming about SPSS or thinking about coding and variables when they're standing in line or doing the dishes, and they think, wow, that's weird. I keep thinking about that. That's actually normal. I've had that said to me many times after, again, teaching over 600 students, that they kind of have these data dreams or SPSS dreams. It just means you're processing the material at a deeper level, even kind of unconsciously, and that's a good thing. That's deep learning. To where your brain's still working on something. Now, you don't want it to be disruptive to your life to where it starts to create some anxiety or make you upset. But it's good to be kind of puzzling over things. That's what's kind of fun about statistics and data analysis. It's a puzzle and it gets kind of competitive. You want to attack it and figure things out, and you don't want to let SPSS beat you or stuff like that. So it can be fun. But this week is logistic regression and other models with categorical dependent variables. So we're going to go over how this works. So basically, just like with linear regression, which is what we learned last week, this goes by a lot of names, okay? So just know that if you see this mentioned in different ways in journal articles or different studies, it's all the same thing. Logistic regression also goes by maximum likelihood estimation. It also goes by kind of the word odds ratios. It goes by binary logistic regression and just categorical dependent variable models. It's all the same thing. It's doing the same thing. Different disciplines will refer to it in different ways, and that's normal. Okay? So, when we look at maximum likelihood regression, or what we call logistic regression, we like to contrast it to OLS, what you learned last week, linear. So remember in that really weird lecture when we were kind of doing these little data points on a graph, and we said we were going to sum the distances between the hypothetical line we're trying to make to represent the relationship between these two things and the mean, and make some estimations and square them and blah, blah, blah. When you have a dependent variable that's a category, you can't do that. Okay? So, for example, I've had students and researchers say, hey, well, linear regression is all fine and good, but what if I don't want my answer to my question in a quantity? Or my outcome variable is whether something happened or not. I can't quantify that. It's a category. So what possibly could I use to analyze that? That's not going to work. So basically, the other side to regression is logistic regression. So if you don't have something you can quantify as a dependent variable, which you would use linear regression for, and you just have something that either happens or doesn't, or assumes this category or that category, very famous yes, no, experienced it, didn't experience it type variables, then you need to use logistic. So basically, if you learn linear regression and you learn logistic regression, you can answer about 95% of all social science questions. Because you're either going to have a dependent variable in some kind of quantity, or you're going to have it in some kind of category. So if you learn those two regressions, you'll be able to do anything, okay? Everybody learns linear. It's kind of the bread and butter regression of graphing this line and having a slope and an intercept and all this stuff. Anytime your data don't meet the requirements of linear regression, you have to do some little adjustment to it. So basically, all regressions in the world are an adjustment to linear regression. So linear regression has a lot of requirements. You must have a dependent variable that's interval. You must have normally distributed data. You have kind of things that you have to meet, all these assumptions in order to run it and for it to be accurate. People love it because it's highly accurate. But what if your data don't quite fit those assumptions and that criteria? What are you going to do? You still want to answer your question, but you need to do something different. So every other regression basically violates one of those criteria. It says, oh, my dependent variable is like this, or my data looks like that. And so it makes it so you can't run linear regression on it. You have to run something else. So whether you do logistic regression or lots of them out there, Cox regression, Kaplan-Meier, hazard modeling, path analysis. I mean, there's seriously like 14 different regressions out there. All of them make some little adjustment to how linear couldn't be run because of the data. That's all it is. So if you learn linear regression really well, you can learn any other one because all of them have kind of that same idea in mind. It's just that the data don't quite fit the requirements. So they just kind of adjust for that. That's all it is. Very simple. Okay, so maximum likelihood estimation, since we can't perfectly make a line that fits the relationship, and I'll show you how this works in a minute, we have to kind of maximize the likelihood of something to happen. Okay, so it's not as accurate as linear, but it still answers our question, which we really like that. So we call it the log likelihood, and I'll explain that in a minute. It reflects how likely it is that the observed values of the dependent variable may be predicted from the observed values of the independent. So remember that famous chi-square statistic you ran a long time ago in those earlier labs? That's very similar to what's going on here. You know, does category membership over here allow me to predict category membership over here? Does knowing this about you let me predict that about you? That's it. That's really all it's doing. And so when you get some output from logistic regression, when you run it in SPSS, you're actually going to find some chi-square stuff in there because it has to run a chi-square in order to do a logistic regression because both of them handle categorical data that give you different categories of stuff. Okay, so this is essentially how it works. I'm not going to go through this in a lot of detail, but it gives you a kind of an overview of how it works. So when you're doing maximum likelihood, it's kind of like doing the lowest common denominator until you get the exact best fit. Okay, so there's a little algorithm that runs in your data, kind of in this little matrix, trying to test how likely something is to happen. Because all statistics really is probability. That's it. It's prediction and probability. It's a mathematic that lets you do probability. So this algorithm will run inside your formula, and it'll kind of test and retest things until it gets the very best line that will work for your data. But here's the thing, the line has to kind of change direction in order for it to fit. It actually curves, and I'll show you that in a moment. Okay, so when you get an estimate or a model, it says, okay, this is the way the data work to make this outcome most likely. So whenever you get a result in logistic regression, it's always kind of the odds or the likelihood of something happening. So it's a little different than the kind of outcome you get in linear. Okay, so here's a famous example. You've studied this in criminology. So we already know that there's a relationship between age and crime. So generally speaking, for young people, as they get older, they tend to offend a little bit more. Peak offending age is about, 17 and a half years? And then there's a steep drop-off around age 24, 25, and you're not offending nearly as much. So we know that's been a relationship that's been around for decades and decades, maybe longer, okay, since we've been measuring it. But here's the thing. So let's say you have some data in a data set that you're going to stick in SPSS, and you want to plot it out, just like you would in linear. So I have age here on the bottom. So, I have 0, 20, 40, 60, 80. So this is how old you are in years. So I have my teenagers, my 20-year-olds, my 40-year-olds. And I can plot out how old everybody is from a question called, how old are you? And I can put all their answers on a graph. Well, what if on that same graph I wanted to plot out a response to, have you committed a crime? Yes or no? And I can put all those answers here. So a yes-no question is generally coded in SPSS as a 0 and a 1, okay? So here's the 0 and here's the 1, yes, no. Well, everyone's age that said, no, I've never committed a crime, it's going to be blah, 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 like a big slew of little responses. And then everyone that did commit a crime that's of this age, blah, 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 another slew of responses, okay? So you get like these little dark lines like that. Well, There are only two possible ways that you could answer that question. Either you committed a crime or you didn't. Okay? Yes, no, that's it. So the problem you run into with logistic regression is you don't have a lot of variation in the answers. You can only have yes and you only have no. That's it. So when you don't have a lot of variation, it kind of breaks the assumption that you can do in linear. Linear assumes you got lots of variation, lots of answers, lots of choices that people can come up with, and your goal is to predict how it varies. Well, there's not a lot of variation here. It's just yes, it's just no, that's it. So, what happens when you don't have a lot of variation? Well, you have to predict how likely a yes or a no is. That's the difference, okay? Because there's just a limitation as to what people can say. Okay, so the only way to graph this out in some kind of line is what we call a sigmoidal curve. So if I were to take my little cursor and kind of draw an S shape, kind of between yes and no, it actually changes direction. So at what point does, the people of this age actually change from a no to a yes? That's the only possible graph shape that could fit these little data plots. I can't draw a line between them, okay? It's not going to work. I only have this answer and the data points in between. You have to actually do like a little curvy S. That's the only way it's going to work. Sigmoidal curve. And we told you with linear regression, if you have curved data or data that changes direction from one response to another, can't run linear. And this is definitely one of those times. So if you have a dependent variable that's categorical, this or that, or this happened and this didn't, you can't run linear. You have to run logistic regression. Okay? So, how do you run it? Well, let's go into SPSS and show you. Okay? So in SPSS, sorry, I had to kind of relaunch this while I was recording. In here, I have two of these open. I don't need two. Yes. It's in the same place as linear. So if you go to, I'm going to move it over. If you go to the File menu and then you hit Analyze and you go to Regression, you select Binary Logistic. Okay? So this is where it lives in the menu. Oh, and I don't have data. Open some data. So it says, hey, I can't run anything because I don't have data. I'm just going to open up the General Social Survey so we have some data. Okay, now then, let's go through Analyze and Regression. Binary Logistic. Okay, so here's the menu that you would normally use. So right here, it asks for your dependent variable. Okay, so you select your variable from the list. Don't forget that famous reset button. If you just barely created a variable that you're going to use, maybe you recoded it into ones and zeros, you may want to hit this famous reset button just to refresh your variable. Let's make sure it's there. So you add your dependent variable, you add your independent variable here in the block, okay? And that's all you really have to do. Now you can ask for other stuff if you want to by clicking on options. You can ask for confidence intervals. I don't particularly like confidence intervals. They're not really useful to me, so I don't do that. But you could if you wanted to. Okay, but at this point you're kind of ready to go. You just click OK and it'll run some output for you. Okay, and I'll show you what that looks like soon. But that's where it lives. That's how you run a logistic regression. Okay. Back to our overview. Here we go. So, this is our famous example. Here's the syntax. You can actually run any regression you want using syntax. You can just copy and paste this from the slide or just type it in to a syntax editor. So remember, anytime I bring up syntax, you don't have to use it. It's just another way to run a function in SPSS. It's not required. It's just kind of like the HTML kind of JavaScript version of going in a menu. That's all it is. Okay? But here's the output you get for logistic regression. I'm going to actually stop the video here and we're going to go through this output in a lot of detail so you can understand what it's creating. But that's just kind of a mini overview of logistic regression, when to use it, how it works. See you next video.